about the kind of cosmology that you can do with Euclid. And basically, I will try to take you in a trip from the promise of this science, basically from the dreams of a bunch of people more than 15 years ago to the present, where this has become a reality. Now we have a beautiful satellite that is launched into space and is taking very nice pictures of the universe, as I will show later on. So let's get started with the trip. But before that, I would like to show this slide that you have seen probably 1,000 times, many of you, but just to set the scene. So basically, we know that we have a cosmological model based on general relativity. This is called the lambda cold dark matter model, that we believe that explains successfully a wide range of observational data from the deep universe and from the primordial universe in particular, but we still have a few open questions in this model. In particular, the main constituents of the model, of the lambda cold dark matter model, are not very well known. We don't know what they are. So we know that there is something we call dark matter. We believe it's a particle we have not detected yet that is responsible for the clustering of and the growth of structure in the universe. We have another component that we call dark energy that is believed to be responsible for the accelerated expansion of the universe, but we haven't detected this dark energy directly. There is no physical evidence for that. So there is I would say, the possible alternative to this model, which is that general relativity is breaking down on the largest cosmological scales, and we have to decide whether this is true or not by exploring further in the universe. There is also the well-known tensions in the measurement of cosmological parameters, in particular the expansion rate of the universe and the parameter that measures the amplitude of fluctuations that we call S8, depending on whether you use cosmic microwave background data or galaxy surveys, okay? This is a significant tension, but you have to think that these two observables, the early universe and the late time universe, basically they use the same model, which is extrapolated by a factor of 1,000 in scale factor, okay? So it's not completely surprising that the model may fail, okay? So we want to investigate and basically settle down these questions for good by exploring a larger volume of the universe with very high quality data. And this is precisely the motivation for Euclid. It's a mission a cosmology mission to study the universe, in particular the gravity and the nature of dark matter and dark energy, okay? So this was a mission that was happily selected by ESA about 12 years ago, and it's a medium class mission. So, at the time, basically when the mission was proposed, there were a number of goals which has, evolved in time, but basically the main science goals are these ones. So we want to understand what is dark energy, whether it's constant in time or whether it evolves in time, okay? So this we don't know yet. And that's why Euclid is going to explore the high redshift universe to see if there is a possible evolution of this so-called dark energy equation of a state, okay? We also want to test gravity. As I said, we want to measure tiny deviations from the predictions of general relativity. And at the same time, we want to test this cold dark matter paradigm that we believe is explaining all the range of observations, as I was saying, and also to constrain the total mass of the neutrinos that we believe now are part of the standard model of cosmology, okay? Especially when we combine it with Planck. And last but not least, we want to improve by at least an order of magnitude the initial conditions, the measurement of the initial conditions of a structure formation in the universe, and in particular, basically constrain the inflationary models that we believe seeded the structure formation in the universe. Okay, so this is the Euclid mission in a nutshell, let's say, in numbers. So the Euclid consortium has grown exponentially since it was adopted. So at the time, there were just a bunch of people, about maybe less than 100 people in the community. And then with time, this has surpassed the 2,000 members. And this is the size of today's galaxy survey collaborations. There are more than 300 institutes involved. It's 13 European countries, so that's basically the bulk of the Euclid consortium. But there is also a component from the USA, Canada, and Japan, which is also contributing to the project. And the main objective of this consortium is to lead the two instruments, the visible imager and the near-infrared spectrophotometer, along with a pipeline, the scientific pipeline that is going to reduce and distribute the science data ready products of the mission, okay? There is also a very important component from industry. Obviously, without industry, we cannot build any instrument. So there are about 80 European companies participating. So there's a clear impact on the economy, on science, I would say, in this aspect. And then in terms of the survey, Euclid will map basically 1/3 of the sky. So basically the cleanest regions of the extragalactic sky with a resolution, a spatial resolution, which is comparable to that obtained by the Hubble Space Telescope. So this is 4 times sharper than any ground survey. The end product of the mission comes basically in 2 flavors. There will be a photometric sample containing more than 2 billion galaxies, basically up to redshift 2.5. And then the spectroscopic sample, which contains about 30 million galaxies. These are emission line galaxies in the range between 1 and 2, as I will show later. Okay. So now, let me just emphasize the fact that the Spanish contribution is very significant and has been prominent since the start. So I would like to mention 2 people that were key in order for Spain to get into the mission. These are Francisco Castander and Rafa Rebolo, so the 2 Spanish representatives. They were there from the start. They were pushing really hard for this to happen. And today, we are basically have commitments to actually deliver something for the project, also thanks to them. So there is a multilateral agreement between ESA and the Ministry of Science to contribute both on the instrument and on the ground segment simulations, okay, the image simulations. So we have responsibilities there. In particular, IC, IFCA, and IEEC in Barcelona are contributing to the design, construction, testing, and validation of the filter wheel assembly, of the near-infrared spectrophotometer, and then the Universidad Politécnica de Cartagena, along with the Instituto de Astrofísica de Canarias, are also contributing to the design, construction, and validation of the electronics of this instrument. Okay, so this is a very important contribution from the Spanish community. There are about 170 researchers, counting everyone in terms of engineers, scientists, across 22 institutions. So this is about, or close to, 10% of the overall consortium. So this is a very significant portion of the Euclid consortium as a whole. And we have a leading role in coordinating both science working groups, like the cosmological simulations in which I'm involved, IST nonlinear, which provides a model, nonlinear model, theory model for the observables, and leading roles in the science ground segment, image simulations, the science data center, one of the 9 science data centers of Euclid at PIC in Barcelona, and then management roles in all the bodies, basically, from science team, Euclid board, editorial board, and speakers bureau. Okay, so it's a very prominent role. Now let me go back to the instrument. So Euclid is optimized for wide field imaging and spectroscopy. It's quite unique in terms of wide field of view with very nice spatial resolution. This is unique. This is showing basically the projection of the visible imager on the sky, so it's wider than the moon, so that you have an idea. So the field of view is 0.7 by 0.7 square degrees. As I said, the visible imager contains 36 CCDs. The resolution is 0.1 arcseconds per pixel. This is very fine resolution, enough to measure the shapes of very distant galaxies at very high redshift. This is an exquisite, I would say, spatial resolution. It uses just a broad band in the visible from 500 to 900 nanometers, whereas the NISP, the near-infrared spectrophotometer, has a lower number of CCDs with lower resolution. Basically, overall, it's a factor of 3 lower resolution, still quite good resolution, and basically has 3 bands covering from 900 to 2,000 nanometers. Okay? On top of that, we have the slitless spectroscopy capability with very nice resolution. So basically, we can combine from this instrument both infrared photometry and spectroscopy. Okay, this is just a quick comparison of how Euclid field of view compares to other surveys. So you see on the right JWST and HST, which are less than 1% of the field of view of Euclid. And then you see that the only survey that actually compares in terms of wide field of view is the Roman satellite that will be launched in a few years, but basically will be complementary to Euclid. It will go to the far infrared. Okay, so nothing really compares at the moment to Euclid in this combination of wide field of view and spatial resolution. So these are the bands Basically commented, so you can see the distribution, the visible from 500 to 900, the two photometric bands of the NISP in the different colors on the right, from 0.9 to 2 microns, and then the blue and red grisms of the spectroscopic part of the instrument that cover pretty much the same wavelengths. Below you see, you see basically the limiting magnitudes for the wide field is 24.5 in the visible, 24th in the near infrared, and the deep field goes 2 magnitudes deeper, okay? And also it goes deeper in terms of spectroscopy. Okay, so just a couple of words on the instruments. I don't have much time, just for you to keep in mind that the visible imager is devoted to getting very accurate images of galaxies and their shapes. So this means that the instrument has to be very stable and very simple, okay? So that there are no moving parts, and that's the bottom line. This is a very simple instrument, okay? On the other hand, the NISP is much more complex because it has to basically conjugate the two kinds of observations, the photometric part and the spectroscopic part. So basically, this has moving parts, let's say, and it has two wheels, one for the filters and the photometry and the grisms. So this is much more sophisticated, and this is the main instrument, again, for galaxy clustering, okay? So 2 instruments for 2 different kinds of science. This is the optical layout, how the beam crosses the baffle on the top left, through the mirror, bounces in several folding mirrors. The basic thing is that it goes to a dichroic that splits the beam. One part goes to the NISP, and then the other part goes to the VIS. But basically, the idea is that both instruments observe the same region of the sky simultaneously, okay? You see on the right how the light path looks on a real picture, let's say on a picture of the real satellite, upside down, but it's a bit more complicated. This is how the satellite looks when it was integrated by Airbus about 2 years ago. You see the baffling system in white, the instruments at the bottom on the left. Then you see the solar panels, basically. You can imagine the satellite revolving in this way as it basically circulates or orbits around the sun solidary to the Earth, and the light from the sun will basically impact the solar panels that you see in black here at 90 degrees, okay? That's how it operates. Okay, let's go for the promise. So this is what Euclid promises to deliver, okay? 2 different surveys. A wide survey covering about 14,000 square degrees in the sky. It's going to avoid basically the Milky Way plane that you see in this Z shape in this projection, and also the ecliptic plane to avoid the zodiacal light, okay? The rest of the sky is the region that Euclid wants to observe for the wide footprint. Okay, and it's going to proceed from the ecliptic poles and advancing down to the ecliptic plane. So in different colors, you see the areas that are going to be covered in the different years of the nominal lifetime of the mission, starting basically from the green around the ecliptic poles and ending in yellow in the 6th year of the mission. So overall, it's 6 years in the nominal mission. I just wanted to mention the fact that there will be also deep fields. They will cover small regions close to the ecliptic poles, around 50 square degrees in total, and this will be used more for legacy science and for calibration. And there will also be photometric information that cannot be obtained from space with Euclid, will be supplemented from the ground, okay? This is very important in order to achieve the science. So we already have covered all the information in the visible and in near infrared from DES, unions, and LSST. So LSST basically covers the south and slight part of the north, and then unions basically on the north, DES also on the south. So we have all this in place, and we are ready basically to combine it with the data from the satellite. This is a summary. I'm not going to go through this, of the Euclid wide and deep surveys in terms of how many galaxies you will get, about 1.5 billion galaxies for the photometric sample, 35 million spectra for the wide survey as well, and for the deep, the numbers go down dramatically, obviously because these are small areas, but still 1.5 million galaxies in photometry, 150,000 spectra in, well, from the NISP. Okay, so let's go to the cosmology and the science itself. So cosmology, as you know, is mainly probed by measuring the expansion rate of the universe and the growth of the structure. Okay, these are the two main things you want to measure. And with Euclid, we can pin them down with two different observables. So the gravitational lensing, weak gravitational lensing, that basically measures the distortions of light rays from distant galaxies as they traverse the intervening dark matter, okay? So that distorts the shapes of those galaxies, and with that we can recover the dark matter intervening between those sources and the observer and the growth of a structure. From galaxy clustering, basically we assume that light traces mass. So basically by measuring very accurately the positions of galaxies, we can actually reconstruct the underlying dark matter in 3D, ideally with spectroscopy, and therefore to be able to constrain the expansion rate of the universe, in particular with the baryon acoustic oscillations in the galaxy power spectrum, and the growth of a structure through the redshift space distortions, so through the velocities of those galaxies. Okay, so let's move to Euclid weak lensing very quickly, just to compare the performance of Euclid with current surveys. So this plot basically summarizes what is the situation. So in the x-axis, you see the redshift depth of all these surveys today, KITS, DES, and HSC, the best surveys for weak lensing from the ground. And you see that Euclid is going to basically outperform all of them significantly, both in the number density, which you see in the y-axis, at low redshifts, but also extending the redshift depth by almost a factor of 2, okay? So this is a significant step forward. I'm not going to talk about all the work that the science ground segment is doing so that you can actually get these clean shapes of the photometric sample of galaxies, but there is a lot of processing involved in order to clean all the astrophysical and instrumental systematic effects before you can actually do cosmology, okay? So I will save you that. At the end of the day, this is the forecast, the projection of how the statistical error bars will look like for Euclid, that you see here in black, in comparison to the current surveys, okay, in color symbols. So the bottom line is that for the overlapping redshifts, basically redshifts below unity, we are basically getting error bars which are an order of magnitude smaller than current surveys, but we are also extending the redshift range, as I said. Okay. How am I doing? Anyway, okay, so I should speed up. So galaxy clustering. So we are going to use this slitless spectroscopy. Basically, this means, in simple words, that we are not going to use predetermined targets in which we put fibers, as it happens, for instance, with DESI, but we are going to observe all galaxies. We are going to get all spectra for all galaxies in the field of view. And this obviously is a new technique that is very noisy in a way. So basically you get these very messy images that you see on the top. Here basically you see, oh, sorry. So we should do like this. So basically you see this, basically these very bright features in columns of the CCDs. These are light dispersed from many galaxies at the same time, okay? So we need algorithms that are able to, from these images, to recover the spectra at every pixel from many different galaxies, okay? And this is achieved because we have the flexibility in the Grism orientations to do this sort of inversion problem. Anyway, I won't go into that. The bottom line is that we can actually use these images to end up with 3D positions of the galaxies, very accurate ones, okay? This is hard, but it's doable. So if we do that, basically we can end up with this measurement of the power spectrum in redshift space, for which we can measure the baryon acoustic oscillations and analyze the full shape that is called of these two-point statistics to constrain the expansion rate and the growth of a structure. I forgot to say that this is on the left how Euclid compares in terms of volume and number of redshifts with all other current or existing surveys. As you can see, only DESI really compares to Euclid in this sense, but actually Euclid is a bit denser over the volume that it occupies. So it's basically the best survey for this, along with DESI, I would say. So this is the $1 million plot in terms of forecasting. It's not yet the data. We hope we get there very soon. So the basic idea is that we are going to combine, as I said, these two main cosmological probes, weak lensing and galaxy clustering. And when you do that, that's the power of Euclid, is the fact that you are going to use probes which are, very small statistical error bars associated to them, but especially when you combine them, you are going to break the degeneracies that affect those probes separately, okay? So basically, you are going to constrain cosmology way farther than with these probes separately. Also, because when you combine, you are less sensitive to the systematic effects that affect those probes individually, okay? So it's both statistically and in terms of systematics that this probe combination is key, okay? So at the end of the day, we're going to get 1% error bars on the basic lambda CDM parameters. This is comparable to the precision of Planck itself. So it's the first time that the galaxy survey is actually comparable in constraining power to a CMB experiment like Planck, okay? And we are going to do better in terms of dark energy constraints than any other previous experiments combined, okay? In particular, for the time evolution of dark energy, this is the first time that we'll be able to constrain it with 10% accuracy. So something that is really precision cosmology, we can say. And obviously, if the lambda CDM model is wrong, we will also be able to see it clearly. And we can pin it down with a few percent accuracy. I'm not showing this here, but this is going to happen as well as part of the analysis of Euclid. Okay, there's much more. I don't have time to go through this. But there is cluster cosmology, it's not the main probes, but there will be about a million clusters, massive clusters to be observed up to redshift 2. This will allow to constrain dark energy by a factor of 2 better than any other cluster survey so far. There is also strong lensing. So we will see galaxy-scale lensing systems of the order of 100,000 at intermediate and high redshifts that cannot be detected from the ground. This is very important. And if we combine it with weak lensing, we'll be able to reconstruct the cluster profiles, okay, from kiloparsec to megaparsec scale, so 3 orders of magnitude in scale. Many other things, AGNs, quasars, massive galaxies like high redshift, all these will be completely, basically, outperform any previous surveys. And of course, just to mention that the legacy value of the mission for astrophysics is huge. Basically, just from serendipitous observations, you will be able to get 100,000 solar system objects, but also you can study local universe, transients, and so forth. There is a lot. I'm not working on that, but this doesn't mean that it's not interesting. There is a lot of legacy value that people will get from this data set. And there are many people, in Euclid interested in this kind of science, and I think it's a very valuable part of the mission. I don't know how much time do I have? 3 minutes, excellent. So just to say a few words about the simulations. I will not talk about this. If there are questions, I will mention later. But this is a very important part of the scientific preparation and exploitation. So we start from state-of-the-art simulations, dark matter simulations. We identify dark matter halos. We populate them with galaxies, with observational recipes. And then we fold in the survey footprint, instrument-specific noise and characteristics, and then with that high-fidelity galaxy mock, we can actually develop the scientific pipelines that later on we will use to analyze the data, okay? So thanks to these mocks and thanks to the degree of realism of these simulations, we are ready to actually analyze the data in the correct way, okay? So this is just giving a few of the specs of the simulations we're using, involving trillions of particles over large cosmological volumes, going to high redshift. I don't have time to go through this. This is the pipeline that is running at the Spanish data center. This is a beautiful, massively parallel platform with which, when we apply this galaxy assignment step to the dark matter simulations, we can generate billions of galaxies in just a few hours, okay? When the mock is calibrated, so the free parameters of the mock are calibrated. But this is huge. I mean, there is nothing like this, to my knowledge, in any other collaboration. Okay, so this is the end product. This is just 1 octant of the sky, 5,000 square degrees, more than 3 billion galaxies, up to redshift 3. Hundreds of galaxy properties per galaxy. make the numbers. And this is just, all galaxies in a stripe through the light cone, the visible and the NISP. I think the quality of the image is not very good. Sorry about that. Weak lensing, measurements in the simulations, comparison with theory. Again, I don't have time to go through this. But we have done the full exercise of determining the power spectra of the 2-point correlation functions from the galaxy clustering and weak lensing. And we have shown that with the models, with the theory models that we have developed, we can actually recover from the simulated data the input cosmology, okay, with high precision. And this is very important because, as I said, this will be used with the real data in the same way. So the fact that we have the theory model, the fact that we have the right simulations, this makes us feel confident that we can now actually analyze the data correctly. So these are all the properties that we have for the simulations per galaxy. You can find this mock at Cosmo Hub, and this is the paper describing the simulations, if you are interested. Okay, 2 minutes for the reality. Sorry about that. So basically, the satellite, as you know, was launched last year in July from Cape Canaveral. It was injected into the Lagrange 2-point orbit. It's 1.5 million kilometers from the Earth. So we completed the commissioning phase, the performance verification. The instruments are performing better than nominal in sensitivity, so people are really, really excited about this. There have been problems, obviously, with the stray light, with the magnificent solar activity that has been recently in terms of X-rays, which was really a pain in the neck for the science ground segment, icing in some of the mirrors. So this has been largely solved by software. So now everything is back to normal, working very nicely. We have 5 months of data already collected. We have pictures like this. So this is the Perseus cluster. This is an image that was released last November. It shows a cluster that is about 100 megaparsecs away with 1,000 galaxies as part of the cluster in the foreground, and about 100,000 galaxies. And for half of them, we can measure accurate shapes, okay? 50,000 galaxies is just one field. And we are going to obtain about 40,000 of these pictures across the nominal survey. If you make the numbers, 50,000 by 40,000, that gives you, more or less, the 2 billion galaxies with accurate shapes, just with this simple exercise. It's a rule of thumb. So basically, the promise, I think, is becoming now a reality, right? There are other images like this spiral galaxy. This is in the plane of the Milky Way, but and it's face on. But we can observe it because we have the infrared channel, right? So we can actually see through the dust, and we can get these very nice images. This is a composition between the visible and the near infrared, and you can do some galaxy evolution studies with it, okay? So I finished with the timeline for the survey. We have started already. The data release 1, including 1 year of data, will be delivered to the collaboration in June approximately next year, summer next year. 1 year later to the full community. Then there will be data release 2 years later in 2027. And then the final data release after collecting the 6 years of data in 2030, if I'm not mistaken. There are discussions whether the mission can be extended if there is fuel and there is money to maintain the mission. So basically, we can extend the nominal final area of the survey, which is about 13,000 square degrees, to complete these 14,000 square degrees that were promised. Again, we want to fulfill the promise. Okay. So I will stop here and will leave you with a few links if you want to get more information or follow the day-to-day activity of the project from the social media. If you're interested in the papers presenting the EROS, the early release observations that I showed, or the papers presenting the mission, they are on the archive. They were submitted last May. Okay, thank you.
So thank you very much, Pablo. It's time for questions. 1, 2 questions. I cannot see from here, so.
Any questions? Here, there's a question. Okay, the extension. Okay, so it's the plan. I mean, this is under discussion. So the idea is that, as I said, because there have been these problems with the stray light and so forth, and with the X-rays, so part of the visible CCDs have been slightly damaged. So this means that the effective area that we can cover in the 6 years doesn't reach the 14,000 square degrees. And therefore, we want to actually, in order to fulfill the figure of merit that I showed in that forecast for the combination of the main cosmological probes, we need ideally to extend beyond the 6 years. So, I mean, the possibility is that we can extend up to 2 years, maybe, and we can go beyond 14,000 square degrees. But this is under discussion of whether, I mean, we want to do that or we want to prioritize some other things, like the deep fields. I mean, there is a wide range of science that you can do beyond just extending the area, right? So there is a scientific discussion going on at the moment in the board, in the Euclid board, to decide what is going to happen with the science team, obviously. So this is not yet fixed, but there seems to be a plan for go beyond the 6 years of the nominal lifetime, yeah.
Thank you. One more question?
Yeah.
Okay.
Sorry, a very fast one. Maybe I misread, but I thought that you said that the data release for the Q1 was November 2024?
Sorry? The release.
The release.
Data release
the
one.
Q1.
So there will be, well, first of all, there will be the Q1, it's called. This is just a small patch of the data that will be released in fall this year. But this is just for like legacy survey science, let's say. Astrophysics, not cosmology. So the cosmology release is data release 1, which is going to be summer of 2025. This is for the Euclid consortium. Internal release, there will be 1 year for the community within Euclid to analyze the data, produce the papers, just 1 year. And then in the summer of 2026, the papers along with the data will be published, okay? So this is very stressful for the Euclid community, but this is the schedule that we promised. Yeah.
Okay, thank you.
So thank you very much, Pablo.
Okay.
We can... And we can proceed with the second talk. The second talk, la segunda charla, va a ser directamente la dará Rafa Guzmán. Rafa Guzmán es profesor de investigación actualmente de Cantabria, del Instituto de Física de Cantabria. Rafa también es, de alguna manera, el investigador principal de la primera misión que está liderada por España, a la que ya pertenecen más de 130 personas en el consorcio, con una tercera parte, por tanto, casi unos 40 científicos y ingenieros españoles trabajando en la misión. So, gracias, Pablo. Gracias.
Bueno, en primer lugar, buenos días. Muchas gracias a todos y especialmente a Minia y al comité organizador por invitarnos a compartir este sueño de esta misión con todos vosotros. Para mí me hace mucha ilusión estar aquí hoy porque realmente este sueño comienza en una misión de la SEA hace 14 años, allí en Madrid, tras una conversación con Carlos Frank. Y realmente os digo que es muy emocionante el estar aquí hoy cuando ya estamos metidos de lleno en la misión. Es difícil competir con Pablo y su charla sobre Euclid, pero intentaré hacer lo mejor posible. So switching to English now. ARRAKIHS was selected as the next F-class mission by the European Space Agency in November 2022 after a very competitive process. We were 19 proposals from all over Europe. There were 2 different phases, 3 different interviews by committees, 1 engineering committee at ESA, 2 scientific committees. And in the end, we got actually the good news that we have been selected as the next F-class mission. F for fast, but for us is more like a fast and furious, because for the last for the last year and a half, for people like Santi Serrano, for Maria Angeles and Elena, and the entire team, actually, it feels already like a 10.5 years. It has been extremely strong pace of work, but we feel extremely delighted, actually, to share with you these results. So in a nutshell, the F-class mission at ESA guarantees a budget of about 175 million euros from the European Space Agency. And they are responsible for the spacecraft, for the launcher, and also for the mission and science operation centers. Now, we in the consortium, we are responsible, well, the consortium is led by Spain, and the original consortium included Switzerland and Sweden, Austria and Belgium. And now this year, we have the opportunity to include the UK and Denmark, Norway and Portugal. In addition, we have a few institutions from Holland and Denmark, plus the United States and Taiwan and Thailand. Now, in Spain, the mission is being led by IFCA in Santander, with a major collaboration and participation by CEFCA, the IEEC, and Universidad Complutense de Madrid, and also some researchers that are participating from Universidad de Valladolid, from IAC and IEA. The main responsibility for the consortium is the science case, also the instrument and the science ground segment. And as you can see in this organization chart, we are very intimately linked to the activities of ISA. And I have to say that over this year and a half, we have managed to get a really, really solid link of collaboration. We don't feel like ISA versus the consortium. We all very much feel like ARRAKIHS. I also want to highlight that this is a mission in which young people, early career researchers, play a key role. And I want to highlight the role of Alex Camazon. He's a graduate student, and he's also the instrument scientist of the entire mission. And this is, again, because it's the young people that is driving with their enthusiasm, their commitment, much of the work that you will see here in the mission. And also, we see this as a training opportunity that within 10 years of the mission, you actually have the next generation of leaders of future M and L class missions at ISA. The schedule is very, very fast. So you can see on the top the spacecraft timeline and on the bottom the payload. We passed phase 0 of the payload in September last year, and only 4 months later we passed phase A. And to the best of my knowledge, I think that we were the fastest ever mission in the history of the European Space Agency to pass phase A in only 4 months. And with huge congratulations from Frédéric Safar, who is the head of the new divisions, of the new missions. I also want to say, because I think it's important for all of you to realize that Spain is leading it through the effort and the support of CTTI and the Agencia Estatal del Espacio, but also with a financial commitment. It's about 45% of the 39 million or so that the consortium is providing that is being committed by Spain. And by Spain is all of you. So what I want to say is that this is an open invitation to all of you to participate in our mission. You have open doors, and we will very much welcome your participation. Now, there are 2 things, I think, that qualify ARRAKIHS as an F-class mission. One is that we have a very well-focused science case that, despite being very focused, has profound consequences in cosmology. The second one is the very high technology readiness level of our technology, because from the very beginning, we joined forces with the industry. Starting with the science case, you can see here that our goal is to resolve the observed tensions of the cold dark matter model at galaxy halo scales. And you can see the example here on the right. This is the so-called missing satellite problem and the plane distribution, or the satellite planes problem, in which what you can see is simply the number of satellites that are observed in the halos of the Milky Way and Andromeda galaxy compared to the actual predicted numbers from CDM, which exceed in a very large amount what you can actually see. But of course, these are only 2 objects, right? 2 halos, Milky Way and Andromeda. Now, on the left, you can see the study of the stellar streams. These are the distraction of some of the satellites due to the tidal forces in gravitational interaction with the main galaxy. And according to CDM, there should be stellar streams in every galaxy halo that we can see. But when you go and look at them from the ground, they can be observed only in a few. So now you have large numbers, but the problem is that you may not be reaching sensitive deep enough. It's not very sensitive. So lack of numbers, not sensitive enough, and that's precisely what we set out to do in ARRAKIHS. So what we want to do in ARRAKIHS is to provide a very, very deep, simultaneous, visible and near-infrared observations of a statistically representative sample of galaxy halos of Milky Way-type galaxies down to an unprecedented surface brightness. And you can see in this plot on the right, we're going to focus on 3 observables: the stellar halo, the stellar streams, and the satellites. You can see the properties that we would like to measure, and from those properties, how we can extract the implications of the physics, the physical processes, both related to the types of dark matter and also the typical mechanisms of baryon physics. I want to highlight one thing. This is the first mission, space mission, that is focused on the study of the ultra-low surface brightness universe. And in order to do that, you really have to optimize three things from the very beginning, from the design of the mission, which is the instrument, the observational strategy, and the image processing algorithms. Otherwise, it's extremely difficult with the standard observatories to actually reach the very, very low surface brightness that we want to reach. And in addition to this, we're actually carrying out an extensive set of simulations, cosmological simulations, to be able to have the proper data to compare with our observations regarding the predictions, not just of CDM with the standard baryon physics, but changing the baryon physics and also changing the flavors of dark matter. So this is in a nutshell ARRAKIHS. This is how we're organizing ourselves during the current phase B. I forgot to tell you actually that the key thing that we're doing right now after phase A is conduct everything that needs to be done in order to pass preliminary design review. This will be in spring 2026. This is the phase B. And as we expect, actually, we pass PDR, then the mission will be adopted, and they select also the spacecraft that will come along with our payload all the way to launch in 2030. So this is in a summary of what we are doing now during the phase B. We start with a particular flavor of dark matter and baryon physics. We produce the cosmological simulations from which we will extract the particular galaxy models. And then we focus on the properties of the three observables, the stellar streams, the galaxy satellites, and the stellar halo. And we define the statistical descriptors that then will allow us to discriminate between the various different cosmological simulations. Now, those galaxy models serve as the input for the mock image code that we have developed, and that also includes as another input the survey strategy. And that's where we put what is the galaxy sample, what are the typical filters, what is the sensitivity and the resolution that we need, what is the offset and detail strategy in the observations that we will take, etc. After producing the mock images in the most realistic manner, then we go through image processing to be able to derive what it is the best image so that we can do the science. And the best image requires an accurate modeling of the background, particularly stray light, so that we can remove it and then see the very, very faint features we want to study. After that, you go into data analysis, and the first thing we need to do is to remove the contamination by the foreground galactic cirri and the background galaxies. And once that we have identified statistically, we don't have a spectroscopy, we can identify the candidates to the streams and the satellites, then we characterize them with the same statistical descriptors that we have defined in theory. We compare the two of them, and from that comparison, we will be able to determine whether we can actually discriminate from the various theoretical predictions, and if so, it will define the figure of merit regarding the limiting surface brightness of our survey, the limiting magnitude, the spatial resolution, and the minimum number of galaxies. Okay, so just showing you a little bit of the work that we are doing in theory. So we're carrying out at the moment 30 very high resolution galaxy simulations in 6 different flavors of dark matter. This is work done by Santi Rocafabrega and his team both in Sweden and in Switzerland. And from this very high resolution, we will be able actually to include 2 more from the Agora collaboration, which is very important because we need to understand what is the uncertainty in those model predictions, and that means that we need to understand what is the systematics associated to the use of different codes in the simulations. So we will use Agora in order to standardize actually these results from the cosmological simulations in all these flavors of dark matter, and then we will introduce different changes in the baryon physics, particularly feedback where it is related to the stellar feedback or to the UV background at the reionization epoch. And then we will go a step further, just extracting those galaxy potentials in order to simulate at a very high spatial and mass resolution so that we can now have a better handling of the thinnest stellar streams and the smallest satellites. Overall, this work will require of the order of 200 million hours of CPU in the high-performance computers. And again, it is a major contribution, part of our legacy of ARRAKIHS to the entire community. Now, why do we need to go to space? Well, what you have here is the state-of-the-art of the work that has been done from the ground on the stellar streams. This is the work by David, Maria Ángeles, and their student Juan Miró. This is taking all the galaxies from the DESI legacy survey, and only about 10% of the entire sample actually showed stellar streams. Why? Well, they're reaching only 28.5, only, quotation marks, only 28.5 magnitudes per square arc second. If you want to test the predictions of CDM, you need to go much deeper, because the key thing when you try to measure an effect is that the size of the effect has to be much smaller than the size of the uncertainties, both on the model predictions and on the measurements. So what you can see here is the detection rate of the stellar streams on the upper right versus the limiting surface brightness of the surveys. And the lines correspond to the predictions of the CDM model. And you can also see some of the representations of our own galaxies that we have modeled in ARRAKIHS at different cutoffs in surface brightness to illustrate the point. So at 27.5, this is what you see, very much no streams. 28.5, this is the limit of Juan Miró's work from the ground. You start seeing maybe one here on the bottom left, 29.5, 30.5, 31.5. At 31.5, every galaxy that we observe, almost every galaxy that we observe, should actually show a stellar stream. And that's the simple test. And this is what we want to do in ARRAKIHS. So we want to reach 31.5 for a representative sample of galaxy halos, and the number of galaxies will determine the uncertainty on the observation. So we need about 75 or 100 objects. And then we will be able to corroborate or not CDM. Because if we only observe in about 60% of the sample, then this will fatal blow to the CDM theory. And that's where our cosmological simulations, named Harkonnen by Santi, will actually kick in, where we can actually then study, if they are not consistent with CDM and the current approach to baryon physics, what is the modifications to baryon physics, or what are the different types of dark matter we need to consider. This is just one of the statistical descriptors that we will use. We have others that we're currently defining, both for the properties of the stellar streams, the luminosity function of the satellites, the distribution of the satellites, etc. Now, the second aspect that I mentioned is the high technology readiness level of our technology that is based on the ISIM binocular camera by Satlantis, which is a company based in Bilbao. The nice thing about this camera is that it has already been validated in space. This, you can see Commander Chris Cassidy, International Space Station, that is just about put the ISIM camera in the airlock to be positioned on the outside of the Japanese Kibo module. Again, this is 2020. At this point, Commander Chris Cassidy was actually talking to King Philippe. It was a very emotional day for all of us. This is the binocular camera. It is a very simple but very powerful camera that we designed and patented at the University of Florida. It's only 3 optical elements. They're all spherical surfaces on axis, so it's relatively easy to align. But despite the simplicity, it offers diffraction-limited imaging over the entire field of view, which is 1.3 degrees, and over the entire wavelength range, all the way from 300 nanometers to 1.7 microns. So now, since the 2020s, Atlantic has validated already, has launched to space 6 of these cameras already, and there will be 3 on their own satellites and a 4th satellite that will be launched in October, mainly for Earth observations. Now, this is the current layout of the payload. You can see 2 binoculars, one in the visible and one in the near infrared, with 4 filters. One very broad filter from 350 nanometers to about 950 nanometers for detection in the visible. Another very broad filter from 950 to about 1.6 microns. And then 2 broad filters in the extremes of this wavelength range, in the blue and in the red. That is the current configuration, no moving parts. You have the periscope, actually, to maintain the same mechanical design, and then the baffle for stellate that you can see up there. Then, in addition to the baffle, you can see these radiators for cooling down. Will be passive cooling all the way to 140, 150 Kelvin for the detectors. We'll be using the H2RG, the same one from Euclid and near infrared. But in the visible, we're actually developing a brand new set of detectors with Teledyne, and this is a collaboration between Satlantis and Teledyne. And these are the next generation of high-performance CMOS detectors, all the way from 200 nanometers to 900 nanometers. The main problem that we're having is precisely the thermal shield, because the Earth is a huge object that is just standing below us. And maintaining the radiation field away from the radiators has been one of the major headaches that we have had so far. Regarding CONOPS, we wish with our heart that we would go to L2, but we were told very clear from the very beginning, there's no money. So we have to be at low Earth orbit at about 800 kilometers altitude. It's asynchronous, 6 a.m., 6 p.m., very much around the terminator. And the field of regard determines the solid angle over which we can actually observe our galaxies, determined by the solar angle and the zenith angle. Now, the galaxy sample, we are using a magnitude and mass limited sample, very much Saga style in the selection, plus additional selection criteria to optimize the observability. Overall, we have 226 galaxies. This is work also done by Maria Angeles. And what we have done is that we can observe these objects for about 150 hours each in exposures of 10 minutes in order to reach the desired sensitivity. And here you see a sketch of how we can do it. So we start in the first observation, target number 1. We're taking 10 observations of 10 minutes. After that, again, the Earth comes into the radiation field. We have to move then to a second object, here target number 2. We take another three images, and then we slew to the third position, and so on, and then we repeat the orbit. At 800 kilometers, each orbit is about 100 minutes, just to give you an idea. And it is very important, in each of the 3 exposures, we dither. And this is very nice because it's part of the observational strategy that I'm telling you is absolutely essential in order to be able to model the background accurately, to be able to subtract it and reach the surface brightness. So here you can see a sketch of how we're doing it. Very much, we are actually pointing the telescope at an offset from the galaxy of about 10 to 15 arc minutes. In each of these positions, let's say number 1, in each of these positions, let me see if I can start again. We're taking position number 1, take 3 dither options. Then the next orbit, we go to position number 2, which is now, again, on the other side of this circle. Then we take another 3 dither options. Then we go to position number 3, and like this all the way 300 times to cover the 900 exposures. Covering the field of view will actually move all around the circumference. And that is what allows us actually to smooth some of the defects in the camera so that we can reach the low surface brightness. Second is the mock simulation. We have what I believe is one of the state-of-the-art of the mock simulation codes to simulate missions in low Earth orbit. This is work that we started at the University of Florida, and our student Alex took it actually to the next level. You can learn all of it in his poster, and I very much encourage you to see it. Alex has been invited now twice, actually, to ESTEC because ESA was so enamored from our mock image code that they want to implement it as part of the tools that can be offered to the entire European community to plan the next low Earth missions. It includes everything. We know intimately the camera. We built it. We have already tested in the lab, from the point spread function to the ghost images to the flat fields. The same thing goes to the electronics. We included both solar system effects, of course, the Earthshine, very, very important. We include the effects of the galactic cirrus, stellar fields, and all the whole background. Okay, so I will have to go a little bit faster. Then, after we have produced a set of 900 images that most realistically actually reproduce the actual observations with ARRAKIHS, then we go into the algorithms for image processing. This is what we call M&M, or Mohammed's magic, because it is absolutely impressive what he can do actually with the set of images that we're providing. And it is not trivial. We start with the offset and dither field because we are now offsetting the image. It will be about 2 degrees diameter. The central 1 degree is the deepest part. That's what we are concentrating in. He will first model the second order straight light associated to the ghost images and to the Earthshine. After doing that, then he will be left with the gradient of zodiacal light, which is by far the main contribution to the background. And after he models and removes the zodiacal light, then we have the point spread function. And that's where the work by Raúl has been also absolutely impressive. And you can see in this animated GIF how he is able actually to model the PSF, and including the extended wings, and subtract the very crowded field so that now you can gain the contrast for the very low surface brightness features that we want to observe in ARRAKIHS. Overall, we produce this image. And from this image, we derive the limiting surface brightness, which is 31.6 magnitudes per square second in the visible and 31 in the near infrared. Again, unprecedented at this level. And I remind you, it is a small camera, only 15 centimeters diameter. And this is a type of size that you can do with the small telescopes in low Earth orbit, and that may open up a new era of discoveries from space. Once that we have the image, now we go into the analysis. And just to finish, just to tell you the work that Elena has been doing, this is just a small patch of the field of view with the segmentation map obtained from GenoAstro. This is just to give you an idea exactly the type of satellites that we're dealing with. So it's tiny little blobs actually in our image. And just to give you the preliminary work by Elena on the completeness functions in the 4 filters. So with this, I just finish saying there's a lot of work to do in order to complete the phase B. I'm just listing some of the tasks that we have to do, both in the instrument, on the science and the science ground segment. But I hope that by the next meeting at SEA, 2 years from now, I can actually share with you all the good news that our mission passed phase 2 and that has been formally adopted to be the next F-class mission of the European Space Agency. Thank you.
So, it's time for 2 questions. We can have 2 questions. I cannot see. Here there is 1 question.
Hi, Rafa. Thanks for the talk. My question will be short because you have a very short time from now to launch date, so you have to work a lot. This is a question out of total ignorance, but I have seen in the fields that you have shown that they were quite populated by stars. Is that a problem, and the fields have been chosen in purpose with this crowdness, or?
Yes, so you're completely right. I mean, stellar component is one of the key contaminations that we have. But we have 226 galaxies within our sample. We only need 75 to 100 to complete the statistic study. So we can actually select our galaxies mainly that they will be away from bright stars. The problem with the bright stars are, of course, the effect of the extended PSF to much larger area, and also the ghost images, because we do have internal reflections in the camera. So this is something that we're doing now in collaboration with Maria Angeles in order to see how we can optimize the outcome by biasing the final sample towards those that will not have really bright stars, not just inside, but also close to the field of view. The other stars can be accurately, as Raúl has demonstrated, modeled and subtracted, and it's actually impressive how well it works. Thank you.
Thank you. Maybe I have a question that is almost mandatory to both of you. The idea is a lot of people working in Euclid, a lot of people working in ARRAKIHS, very common goals in some sense, so dark matter nature. The question is, can the science of ARRAKIHS be modified during these 5 years, expecting the first results of Euclid? Or do you have some working groups working in common? Can you explain just quickly on that, but interesting?
Yes, so let me see, perhaps I can show you something. So first of all, I mean, we come in the wake of Euclid, the major cosmology mission at ISA. And of course, just this. And of course, you can see the beautiful images. It's extremely difficult to compete with Euclid on point sources. It's unbeatable. However, we are focusing on surface brightness, and that is the complementarity between the two surveys. So what we have done, there are about 2/3 of the people in ARRAKIHS are already working in Euclid. We actually started a joint team that is sponsored by the Space Institute in Switzerland, so that we are going to be working on the complementarity of ARRAKIHS and Euclid, and also how we can help to do, to improve even their analysis of the local universe. They can do a fantastic job actually in the local universe. But even in the first meeting that we had, you can see the comparison between the published values in surface brightness, this is Jean-Charles Quilland paper, and the current values that we are deriving. And again, the goal is about to reach of the order of a factor of 10 deeper than Euclid in the visible, and between 15 to 25 times fainter in the near infrared. And here just a very quick just comparison of the same galaxy on the bottom, how it could be seen with Euclid and with ARRAKIHS. And again, how important it is just to go. But we're collaborating together, and our goal is to show this in a joint paper that hopefully we can publish in summer next year.
Thank you very much. Thank you. Thank you again to Rafa. And we can go to the next talk. I was looking for you. So the next talk will be here. Someone is doing for you. So great. Next talk is by Vanessa Graber. Vanessa is also from Barcelona. Is from the Institute of Barcelona and IEEC. And this moment she is talking us about this pulsar evolution news, on the science of the pulsar evolution. So thank you very much.
Thank you very much. So I'm going to give you a bit of an overview of a new research field that we sort of have started working on in the last 3 years at the Institute of Space Sciences before I moved to the University of Hertfordshire in February. So to really start this entire story, I have to start telling you a bit more about neutron stars themselves. So neutron stars are born in the supernova explosions of massive stars that have something like 8 to 20 times the mass of our sun. And you can see an artist illustration of what we think this neutron star actually looks like here on the right-hand side. So I really love neutron stars because to me they're the ultimate physics laboratory because they really combine many extremes of physics. So they have masses between 1.2 to 2.1 solar masses, radii the size of a sort of large city, periods between 1 millisecond and typically something on the order of 10 seconds, and very strong magnetic fields that can reach up to 10 to the 8 to 10 to the 15 Gauss. Just for comparison, the Earth's magnetic field is about half a Gauss. So we are several orders of magnitude off of this. And because of the fact that the neutron star's rotation and magnetic field axes are actually misaligned, these compact objects can really emit radio beams very much like a lighthouse. So the sketch that you see on the right-hand side sort of illustrates what the neutron star that we just saw in the artist impression really looks like if we think about this in terms of a more physical picture, where we have the magnetic field axis here and the rotation axis here, and you see this typical dipolar magnetic field. And this lighthouse radiation really means that if this beam sweeps over the Earth or our radio telescope, we can see this increase, and we can see these individual pulses of our neutron stars. So what we can do, because of the fact that this very periodic radiation actually reaches us, and we are able to really very precisely measure this very stable process, we can not just measure the periods of our neutron stars, but also the change of these periods. So we can measure period derivatives. And we typically plot this in what we call the PP dot diagram. As I'm going to show quite a few of these, let me quickly explain what this is. So we have the period on the x-axis and the period derivative on the y-axis. We typically plot these in log scales because we do cover quite a lot of orders of magnitude in period and also in period derivative. And the initial pulsars that we detected, so those are the neutron stars that do emit these regular signals, are the ones that you can see sort of in black here. Those are the ones that emit in radio. But we now also do see these individual neutron stars not just pulse in the radio, but also across the electromagnetic spectrum, specifically in the X-rays, which are the ones that you see on the top right, and the individual purple dots you see here, which are the gamma ray pulsars. So at the moment, we know roughly 3,500 of these, and we typically plot these in this PP dot diagram because it really helps us identify individual classes of neutron stars and really try and group them together and really understand if there are certain similarities or differences. But yeah, so we do group them, and this is sometimes referred to as the neutron star zoo. So we have these individual classes, and there's specifically one that I want to highlight on the top here. You can also see these diagonal lines here that give you an indication. It's not a true measurement, but it's an indication of how we can relate the period and the period derivative to the magnetic field strength. So you see that these are really high magnetic field objects up here, and this is like the kind of class that we call magnetars. So in difference to the radio pulsar population that you see here in black and the gamma ray pulsars that you see in purple that are driven by their rotational energies, X-ray emitting magnetars are really powered by the magnetic energy reservoirs. And they're typically discovered not initially through their radio radiation, but because they actually undergo really strong outbursts and show these flares and really energetic phenomena. And then once we have seen these flares, we can go back and actually also see the emission of the magnetars in quiescence and their regular behavior. Now, if you look at this kind of picture that we have here, it does sort of look like there's a bit of a cutoff here to the right-hand side, which is the sort of 10 seconds that I mentioned earlier on my last slide. So we can sort of like ask ourselves, is there a physical reason why we actually cut this off here? Or is there some other kind of observational bias that can cause this to happen? Now, I'll start with the theory side. So I'm a theorist, so I want to ask the question, is there really like a physical reason why I might not actually have these objects move to the right? And to really understand what the distribution of the stars in the PP dot plane looks like, we modeled the magnetorotational properties, so the magnetic and the rotational properties of these neutron stars using what's called pulsar population synthesis. So we've developed a new code at the ISA in the last couple of years where we really try and like put all the new elements of physics that we currently have, the state of the art, so to speak, together and try and really like develop the new code for population synthesis to use in the next couple of years. So what we do specifically in this case is that we solve two couple differential equations for the period and the misalignment angle, which is the angle between the rotation and the magnetic field axis. And we also extract the magnetic field from state-of-the-art simulations that have been done in the last couple of years, and Nandaria's group as well. And what you're going to be seeing here on the right-hand side is this spin period derivative diagram, but I'm going to be showing some of the tracks that we do evolve for our stars in this picture. So we start with our individual neutron stars on the top left here, and you see they have different types of initial periods and magnetic fields depending on the kind of like Monte Carlo approach that we use. And you see they do sort of like first evolve diagonally along these constant magnetic field lines, but then at roughly something like 10 to the 6 years, they actually start to bend down. So they do evolve eventually vertically in this period derivative diagram, and this is really due to the fact that we can model the neutron star interior in a realistic way as a resistive fluid. So we do have some kind of description specifically for the outer neutron star interior, and if we do this kind of like best physics approach that we have right now, these stars will really bend down, and it's very difficult because of this field decay to really like move beyond the 10-second kind of like limit that we have right here. So if we just look at this kind of picture from earlier, if we put our data points on top, you see there's sort of a physical reason why we think if we put all the best physics in at the moment, then there is really like some kind of argument that we shouldn't see anything to the right. Now, before I move on to the long period sources, which is sort of like the suggestion there is something to the right here, I want to quickly mention how we actually have to detect pulsars in specifically the radio. So in the X-rays, we do not really have any constraints on how much to the right we go, but in the radio, we do have some issues. So specifically, to find periodic pulsar signals in very noisy backgrounds, we really have to do quite a lot of tricks, I would say, and we have to use very sophisticated algorithms to really find these signals, because every single microwave, every single telephone, every single satellite, and so on, as we already heard yesterday for SKA, really produces a lot of background, and we kind of like have to hear a very quiet voice in a very loud, shouty room to really try and identify these signals. So we have some kind of like multi-channel search data from our telescope. And the first thing that we have to do is we have to correct this for the dispersion of the signals. So if a pulsar is very far away from us and the signal moves towards us, there is different types of delays that different frequencies will experience as a result of the electrons in the interstellar medium. So we have to first de-disperse our signal, and then we end up with this time series that we then, depending on the algorithm that we use, first of all, typically Fourier transform, and we get this kind of spectrum where we see some kind of like spikes that give us some kind of like candidate frequencies and the harmonics. Typically, we don't just do this for one DM because essentially this is like related to how far the source is away from us. We typically don't know this, so there's lots of trial DMs that we run this through, and we do this kind of iterative loop at this stage. Once we've decided, okay, we've tried enough of our DMs, we're going to like use the best candidate frequencies, and we're going to fold our individual radio data. What that means is we're going to use the frequencies, turn them into like periods, and we're essentially going to take chunks of our time data, stack it on top of each other several hundreds to thousands of times, and if there's a signal in there, we're essentially going to enlarge this signal, and we occasionally get out something that looks like this on the bottom right here, which is a very typical average pulse profile that's going to be very stable for a given pulsar in the radio band. So the problem is really like if we use these FFT-based methods and other traditional search techniques, because there's also more advanced versions of the fast folding, or the folding algorithms, which is called the fast folding algorithm, or also single pulse searches, they're really struggling to detect sources above 60 seconds, because there's a lot of red noise to the side, so actually finding these long period signals in the data is really hard. So this is why this picture that we had initially here, as well as here, was sort of consistent, I would say. So people weren't really like trying to like move to the right because we didn't see anything, but we also didn't think physically that there was any need to look there. However, there's a second way that we can determine pulsars, of try and find new sources, which is that we can find bright candidates in imaging surveys. So we essentially can take advantage of radio interferometers and produce continuum images to find periodic signals in the image domain. So this is one of the individual tiles of the Murchison-Wildford array, which is one of the precursors for SKLO that we saw also yesterday. And we can really then look for signals that sort of have like a larger period than typically a few seconds in this image domain, and then try and confirm these actual signals that they're really there in the data using the Heim time resolution time series that we have also used to produce the images. So because of this averaging in the image domain, we can't really extract pulse profiles to identify individual pulsars, so we don't really know exactly what the pulses look like, but we have other types of information such as the spectra or the polarization to really try and identify those signals that are not RFI, but they are the individual pulsars. And this method is really useful because it's not limited to 60 seconds, and we really have like no problem to going further to the right in the PP dot diagram that we just showed us, or I just showed you earlier. Okay, so I'm going to talk about two specific sources, the first two ones that Natasha Hurley-Walker, several of our collaborators in Australia, discovered. And the first one is an ultra-long period transient that we refer to as GLEAM-X, J1627, that was active for 2 months in the past 20 years. And it's got a distance of roughly 1.3 kiloparsec with those galactic coordinates. And this source has an emission of 18 minutes, and a really variable pulse profile. You can see individual pulses over this 2-month period in 2018 here on the right-hand side. And the thing that really like sort of made people thought of or think of pulsars or neutron star pulsars to start with is the fact that the source is really strongly linearly polarized with roughly 90% and has a duty cycle of about 5%. The duty cycle is essentially the fraction of our individual period where the pulsar is on. So it's just the width of the pulse over the total pulse period. And these numbers really, if you're a pulsar person, these numbers really remind you a lot of what people know from normal radio pulsars, but also of FRBs, for example. So when this was discovered the first time, obviously the first thing that you do when you don't know what is going on, you use other telescopes and try and find the signal and try and really narrow down the source. by using other kinds of wavelength information. And deep X-ray limits in quiescence, once the source was off, when we compare those to other magnetizers that we currently know, it would really suggest that the source is really too cold to have a magnetostrength crustal magnetic field. So this doesn't really look like any of the magnetizers that we have right now. And at the same time, deep infrared and optical limits really rule out that this is a white dwarf in a binary with a main sequence star, and I will get back to these kind of like hypotheses in a little bit again. Now, the second source is in some sense really similar, in other senses really different, because this is one that wasn't just on for like a certain time period, but it's actually been continuously on for at least 35 years, because this is how far we could get back, go back in imaging surveys. So the very last one down here is from 1988. It's a bit further away, and it's got a very similar period with 21 minutes, and again, really variable pulse profile. It's got a slightly less linear polarization, but still quite a lot. It's also similar to pulsars and a somewhat larger duty cycle. And you can see the source in the actual image domain here. Now, different to magnetizers, which I said earlier, is magnetizers typically have outbursts, but this source is active all the time. It doesn't really show any X-ray activity concurrent with the radio emission like we would want for magnetizers. And currently, we don't really have proper infrared and optical limits, because the source is actually too far away for us to rule out a counterpart at this stage. So the question is really, how many of these sources do we now have? I just showed you two. We now have 6 new ones since 2022, and they all have periods greater than 60 seconds, so it does seem like they are more common than we initially thought. This is from a plot from just last week where CHIME detected this source here. This is a 420-second source, and I'm really excited about follow-up observations of this, because this is actually the closest one of these with 170 parsec. So I'm really excited to see what's going to be found out about other wavelength information about this source in the next couple of months. So yeah, they do seem to be really common. Some of these are normal pulses, like these two down here. There's also magnetar up here that we've already known for a little bit longer that doesn't have a radio counterpart. But for the other ones, the other 4 here at the moment, we really don't know what they are. Are they neutron stars? And if they are neutron stars, I showed you earlier this like simulation of our best physical knowledge that we have right now. Really, how do we make them happen? So the first thing that we can look at to really try and narrow down what's going on is we can look at this so-called radio transient plane, where we plot the pseudo-radial luminosity versus the product of the observing frequency times the variability timescale. And you see that there is this shaded region down here. Those are the regions where the brightness temperatures are too cold for really to the sources to have coherent radio emissions. So these are the ones we identify with incoherent emission processes, and these are all the ones with coherent radio emissions. And our long period transients are somewhere located here, and you see they're sort of close to the radio emitting magnetizers in green, and the normal radio pulsars here in black, and those are the fast radio bursts up here, but they do sort of cover a slightly different parameter space. Now, if this is a neutron star, what can we do? So I said earlier, this is our best physical knowledge, but this doesn't necessarily mean that this is the end of the story, because we might just be missing some physics. So we played around with different ways we can modify our state-of-the-art population synthesis code to really try and see how much can we make this stuff go to the right. So the first thing that we did is we neglected magnetic field decay, and we tried to really see if we can make some of these ultra-long period neutron stars with sufficient energy to match the observations. And this is another of these population studies where we have the initial population in gray. The yellow dots are what we observe, and the green 2 populations are the final populations, and the dark green ones are the ones that actually point the radio beam at us so we can observe them. And you do see there is some at the sort of like 10 to the 3 period level. But the problem is, if we look at their rotational energy reservoirs, which is what we really would want to really get the kind of luminosities that we observe, you see those dots here, and they're kind of above what we would want. So we really can't make these neutron stars, in this case, with sufficiently large energies. Another way that we can make long periods is by invoking fallback accretion. So we can have these scenarios where after the supernova, not all of the material is becoming unbound, but some of it has angular momentum, and when it falls back onto the compact object, it forms an accretion disk, and this accretion disk can interact with the central compact object. And specifically for some realistic fallback accretion rates and strong magnetic fields, we can enter what this so-called propeller phase, which is essentially a state where the matter is accreted into the closed field line region of the neutron star and hits the centrifugal barrier and is then subsequently flung out, like in a propeller, that acts as a really strong torque onto the neutron star. It can really like get us to these very long periods. And we do manage to, like, so this in this plot, this is the parameter region where we can make basically this gleam source happen. It's the very same thing for the other sources. I didn't add a plot for those in the interest of time. But we need sort of like mass accretion rates that are very comparable to what people have found from core collapse supernova rate and moderately strong magnetic field strength. So this does sort of like fit the picture. The problem is we can again try and plot their rotational energy reservoirs. And the problem there is, again, that we do not really have anything that's above 10 to the 27 ergs per second, which is what we kind of would need to make these observed long period transients happen. So the neutron stars don't really work in that case unless there's really some physics that we don't really know about yet. And what is another kind of like system where we think this might happen? So in the transient plane I showed you earlier, the white dwarfs were on the bottom right. So we don't really know how white dwarfs can make the kind of emission happen that we see here, but it is definitely worth exploring a white dwarf scenario because it is the other kind of like compact object that we know exists a lot of in the galaxy. So we had a look specifically at the isolated magnetic white dwarf population. There's roughly 600, and we just used our population synthesis code to model the white dwarf population by just adjusting the individual parameters for the neutron star. So we assume it emits exactly like a neutron star, but we just correct for the fact that they have a larger size and a smaller mass. Now, this is exactly the same plot as earlier. We have an initial period distribution that is given in gray in the back. And because of the fact that white dwarfs by birth already like have a much broader and like period distribution that goes to the right, we do recover lots of sources that actually do hit our typical like 1,000 to something like 10,000 seconds. So there's very little overall evolution in terms of like dipolar spin down because the magnetic fields are a lot weaker in this case. And in this case, we would also end up with E dot values because of the fact that the moment of inertia is different, that does sort of like get closer to what we actually observe. However, we actually don't know a single isolated magnetic white dwarf that does emit coherent radio pulsations. So we currently don't know, and we know a lot of white dwarfs, specifically now that we've found a lot with Gaia, so people have been doing follow-up in the radio, but we don't know a single source, okay? And the typical idea, or people thought this isn't actually expected, is because of how we imagine coherent radio emission to proceed. So typically, if we look at a neutron star, what we think is happening is that the radio emission really comes from the rotating magnetosphere, where we have some kind of like potential gap above the polar caps that accelerate particles and then produce this cascade of electron and positron pairs. And to really make these cascades happen, which are sort of like the necessity for radio emission, we have certain constraints on the periods, the magnetic field strengths, and the geometry. So we have what is called depth lines that I'm illustrating here on the plot on the right. So it's very similar to our period derivative plot earlier. We just have plotted the magnetic field on the y-axis. This is the population of all our neutron stars that we saw earlier. The stars are the magnetars. And we have this, what we call the death valley. So these are individual like magnetic field lines, death lines, that sort of like tell us if we are above those, we allow radio emission. If we are below them, we have ceasing of radio emission. So if we are below that, we wouldn't necessarily expect the sources to be emitting in radio. And we have this death valley, as I just said here, because there's a range of like field strengths and geometries that we can look at. So the top one is for a pure dipolar magnetic field, and the bottom one is for a very multipolar magnetic field. And you see that these sources, as well in the neutron star and in the white dwarf case, these are all the magnetic white dwarfs, we really struggle to explain them with this standard picture. Now, in the last 2 minutes, I'm going to have a chat about the final scenario that we think in principle could explain this, which is the binary white dwarf scenario. So we currently have 2 radio-emitting white dwarf systems. That's the binary system Scorpii, which has a period of 1.9 minutes, and it's in a 3.5-hour orbit that we've known for about 10 years. And a new source, J1912, that has a roughly 5.3-minute period and is in a 4-hour orbit, so it's very similar. That was just discovered last year. And both of these sources have an M dwarf companion And if we look at the plot that we just had on the last slide, I've done a cutout of the magnetic white dwarfs. This source and this source, those are exactly those two accreting systems. So their spin down is, in the AR-SCO case, is sort of partially compatible with the dipolar spin down behavior. But in both of these cases, we really see a strong component in the emission that's due to the interbinary shock with the wind of the companion stars. So it does sort of like suggest that you kind of need a companion that produces a wind to really increase the charge density in our magnetosphere to really make this kind of like pulsation or radio pulsation happen. So I said earlier already that a similar origin is really ruled out by observations for the GleamX source. It's not ruled out for GPM. And in principle, the GleamX source could also still have a lower mass companion. But we really, if we want to make this connection stronger, we really need more than two sources to really look at something on a population level. So currently, this looks promising, but there's still a lot of open questions, really. Okay, and with that, I'm going to conclude. And just want to highlight again that in the last 2.5 years, we had these recent discoveries of ultra-long period radio sources that really suggest that there is quite a few coherent transients that are emitting with periods larger than 60 seconds that have been missed by traditional search pipelines. So these sources, as I hope I convinced you, really challenge our understanding of neutron star pulsar evolution, radio emission processes, and white dwarf properties, and we still don't really know what's going on, but it's also really an exciting time to be working in this field because we really have like lots of interactions with multi-wavelength observers, because that's really like a crucial part of the answering the question, I would say, and also with the white dwarf community to really try and understand what the origin of these radio sources is. Okay, thank you very much.
I think yes, you have convinced us that there are great challenges both in the theoretical and also in the observational domain. So it's time for 1 or 2 questions. 1 or 2 questions. I don't know if there is someone. Cannot look. Someone. There is 1 question up. Okay.
Yes, well, thank you, first of all, for the nice talk on what I think is a very interesting topic. My question is, have you also investigated the possibility of the beam opening angle producing an observational bias? You probably know that some theories say that the slower the object rotates, the opening angle may be smaller, and therefore it just may be that we don't cross the beaming of the white dwarfs in this case, that we may not see them.
Yeah, so actually you might see that there's individual numbers here for 2 and 4 and so on. So we've run quite a few different types of simulations, so I only showed 2 of these scenarios. But we did indeed explore if we could make the angle wider or smaller, how that really would really affect the kind of like numbers that we get. So in this paper, if you have a look at this, there's a table and we vary numerous things. And the answer is, it really doesn't really make that much of a difference, mainly because of this picture. So we still don't have an E dot value that's significantly high to really explain these sources. So it does make a difference, but it doesn't really solve this kind of issue here. So there's a detection bias, definitely, but it doesn't really give you the energies that we actually need for these sources.
Thank you. Thank you. 1 more question here, please. 1 more question.
Thanks a lot, Vanessa. So I have a question related to the PP dot slide that you showed. So you showed some simulations where basically there was this change at around 1 million years, but it seems like there is actually a trend with age or with period. I mean, it's not exactly at 1 million. So what is causing that dependency? So, I mean, if my eyes kind of see a straight line that going, you know, as we move in spin period towards the right, it happens earlier, this turnover. So what is the reason for that?
Okay, really good question. So there's sort of like, if we model the magnetic field evolution and specifically the neutron star crust, there's 2 mechanisms that we have to factor in. One is ohmic dissipation, which is like just a mechanism that is sort of like independent of the environment. It's just determined by essentially the microscopic properties of the electrons, and that really has like a fixed decay time scale. But there's a second mechanism that isn't dissipative, which is the Hall effect, which rearranges our magnetic field in certain ways and basically moves the field from larger scales to smaller scales where it then can decay, and that's actually magnetic field strength dependent. So the Hall effect is stronger, or the Hall time scale is shorter for magnetars on the top right here. So that's why for those sources the field actually decays a little bit on shorter time scales because of this combined interaction between these two different mechanisms. Yeah.
Thank you very much. So,
thank you.
Thanks again, Vanessa. Podemos pasar ya a la última charla que yo creo que va a ser muy amena. Estamos hablando ahora, en este caso cambiamos completamente de tema. Va a ser José Manuel Vaquero, que directamente de Universidad de Extremadura nos va a contar sobre manchas solares desde un punto de vista histórico. En ese sentido, yo quiero aprovechar mis 3 segundos de alguna manera para deciros que justo el año próximo va a ser los 100 años, por tanto, el centenario del nacimiento de la doctora Asunción Catalá, que durante el año 1957, por tanto, de manera muy histórica, sacó 4 imágenes de las manchas solares diarios durante el año internacional geodésico de toda la colaboración. Por tanto, es un tema interesante verlo desde el punto de vista histórico y desde el punto de vista científico que eso acarrea. Gracias.
Thank you very much. Muchísimas gracias a Minia, a la Sociedad Española de Astronomía, por este magnífico encuentro. Y bueno, cambio al inglés y comienzo mi presentación, pero que sepa el público que estoy muy agradecido. I am going to speak about the records of observations, and I would like to start with this image of this petroglyph. It is an engraving in a rock. This is located in the Chaco Canyon, in the wilderness of the southwest of the USA, and this is a typical representation of the Pueblo culture, more or less 1 millennium ago. My colleague, Professor Melville, proposed that this is a representation of the solar corona during a total solar eclipse. Why? Because if you compute the path of the solar eclipse of the 11th of July in the year 197, the path crossed the Chaco Canyon, just more or less in the time of the datation of this kind of petroglyph. I am basically, in a nutshell, I am a climatologist interested in the solar activity, and I was very interesting to study the solar activity during the medieval climate anomaly. Then, by this reason, I called to Melville, explaining, I can check if your suggestion is false, is erroneous, because the solar corona is very different. The shape of the solar corona is very different from a minimum of solar activity or in a maximum of solar activity. You can see, for example, some drawings during the minimum. This is the sunspot number, the solar cycle. During the minimum, you have these equatorial streamers, and in the maximum, the shape is quite different. Obviously, this is a corona of a maximum. Well, you can see in this figure the different solar maximums, and exactly they are a solar maximum just in the date of the eclipse. Therefore, maybe Professor Melville is right, and this is a representation of the solar corona 1 millennium ago. In fact, you can see here maybe the first coronal mass ejection recorded in history. for me, this is something incredible. But the referee too had other opinion, and then this result was not published in a important journal, was published in a minor journal, if we can see polite, Mediterranean archaeology. Well, this is an example of the beautiful things that we can find in the history. This is more or less the index of my presentation. I will talk about the Maunder minimum as an old paradigm of the solar terrestrial physics. Obviously, the sun was not the origin of the Little Ice Age, and the sun is not the origin of the global warming. I will speak also about the measurements of solar radius, and we will visit briefly San Petronio in Italy and San Fernando in Spain. I will speak obviously about the sunspot number. That is the classical example of the use of this kind of records. And finally, I will speak about the first prediction of space weather that was published in Cádiz in 1818, a lot of time ago. Beautiful picture. This is, if you read a book about the Maunder minimum, normally you can see this picture or other similar. This is Hunter in the Snow by Pieter Bruegel the Elder. And this is very nice. Europe during the Little Ice Age. But there are a problem. You can see the date. The date is 1 century before the Maunder minimum. This does not agree. The sun is not the responsible, the origin of the Little Ice Age. 48 years ago, John Eddy published this seminal paper about the Maunder minimum. And some colleagues think that this paper is in his midlife crisis. In the last 10 years in the community, there are two opposite visions. The first, Nadezhda Zolotova and Dmitry Ponjavin, established that the Maunder minimum is not as grand as it seems to be, and in other side, a big part of the community think that the Maunder minimum was indeed a grand minimum. The idea of Nadezhda Zolotova and Dmitry Ponjavin is very nice, because obviously the observations made by scientists also depend of the ideas of the society in their time. Then Nadezhda established that the astronomers in the 17th century are expecting round spots because they are looking for planetary transits. Yes, it is really interesting. We can jump this for questions. However, if you go to the historical documents, you can find things like this. This is a sunspot observed by one of the Cassini in the Maunder minimum, and this spot has a hexagonal shape. How it is possible? Well, you can see this image in 2016, and you can see also a spot more or less with a hexagonal shape. Therefore, you can find in historical documents round spot and also other spot. I think that Nadezhda is round in this assertion. It's very interesting that the idea of the modern minimum is a long period, more or less from 1645 to 1715, without a spot, or very, very few spots, without the solar cycle. But if you choose the data in the Hoyt-Schatten original database, and you choose subset of this database, subset based in quality criteria, you recover the solar cycle during the modern minimum. And this is very interesting. And this solar cycle is shorter, 9 years approximately, not 11 years. You can see here in active day fraction, or reconstructing the sunspot number, you can see the solar cycle during the modern minimum. We started a revision of different historical sources to study the modern minimum. For example, this very beautiful book is the Machina Echolestic by the Poland astronomer Johann Hevelius. And you have a chapter in this book, an appendix really, with very detailed sunspot observations. There are also very detailed sunspot drawings. You can see, for example, the first line, the day 26 of 1642, October, in the sun, no spot appeared. A day with zero spot in the sun. Another important historical source is the Selenographia, also by Hevelius. This is a very famous book because it's the first scientific treatise about the moon, with a very beautiful drawings of the moon in different days. But in the appendix, we have a very important collection of sunspot observations and sunspot drawings. You can see, for example, in this English translation, it has been carefully determined its magnitude, proportion, and distance, and its color, density, nuclei, umbrae, and another element of this style. And it's really, Hevelius invented, created a lot of different words to refer to sunspot and facular regions. In brief, after this revision of the solar data during the modern minimum, we think that the order of magnitude of the sunspot number during the modern minimum is here, not in the extreme of proposed by Solotov and Ponjabin, not the idea of Hoyt-Schatten without the solar cycle, more or less around 10 in the sunspot number. Note that it's very important that the reconstruction of isotopes, the high resolution reconstruction with isotope very recently, two years ago, agree with this idea. We go now to Bologna, Italy. This is this nice figure by Paco Bellido, thank you very much. It's the meridian line of the Basilica of San Petronio. At the midday, you can see the sun in crossing this meridian line. And the Catholic Church used these huge cathedrals as a camera oscura, as dark room to study the astrometry of the sun. Fortunately, an Italian astronomer, Eustachio Manfredi, published all the data in a book. Then you have only use a machine-readable version of this data, and you have here this data from, no tengo las gafas, from 1665, todo hacerse viejo, to 1737. You can see that the series is very noisy, but in this part with a lot of observations, you can see clearly the variation of the solar radius depending of the Sun-Earth distance. This is the apparent solar diameter. Okay. This is very interesting because we can compare the data during the modern minimum and the data in the 18th century. If you analyze these two subsets of this data, we conclude that there is no difference between the solar diameter during the modern minimum and for the subsequent period of observation. And from the point of view of the astrophysics, this is a very astrophysics and geophysics, this is a very important result. We jump to Spain, to San Fernando. This is the observatory of San Fernando in early 19th century. And in this observatory, astronomers made astrometric observation of the sun during centuries. We have a lot of information about the historical instrument use, and this is very, very useful to make the correction to the raw data. The result is here. We undertook a time-consuming task to locate and recover a lot of observations. Note that the archive, the historical archive of this observatory has more than 4,000 boxes of documentation. And this is a tarea de chinos. And you can see our final result. These solar observations are evidence that the solar diameter did not change in the last quarter of millennium. Nobody expects other thing, but these are observations. It is not theory, it is not model, these are observations. We can now speak briefly about the sunspot number. In 2015, the situation in the community that we have two different series of the sunspot number for the last 4 centuries, based in telescopic counting of sunspots. The group sunspot number by Hoyt and Schatten with the modern minimum, and the international sunspot number in the tradition of Rudolf Wolf in red. The idea was to establish one unique time series to represent the solar activity in the past. And I think that more or less we did it. You can see using the ideas of Rudolf Wolf, the red line, the sunspot number, using the ideas of Hoyt and Schatten, the group number, and more or less agree. However, I must to say that our attempt was a disaster, because from one series we have now a lot of different reconstruction of solar activity in the past. During the last 2 centuries, all these series are very similar, but in the 19th century and in the 18th centuries, the time series disagrees. And this is due to the data. You can see in this panel the networks of overlapping observers, and we have overlapping observers in the last two centuries, but we have a very poor statistics in the 17th and 18th centuries. We can also obtain the butterfly diagram with this important asymmetry during the hemispheric asymmetry during the Maunder minimum. Well, the key is in the data. We publish a revised collection of the sunspot graph numbers, and our next main goal is improve this revised collection. We are very interested in observations during the 19th and 18th centuries. We are looking for a long series of observations to obtain good statistics, and also we try to improve the database also with obtaining the number of individual spots, the sunspot position to improve the butterfly diagram. We recover also sunspot area and, of course, sunspot catalogs. Well, we have made a lot of work, and I will only present 3 examples briefly. The first example is about the first telescopic observations in the Galileo times, revising the publication made by the Jesuit Christopher Scheiner. This is the situation in our revised collection. The solar cycle the shape is not very good, but after our revision, you have a shape more realistic of the solar cycle. We are also very interested in the Dalton minimum in early 19th century. This set of small amplitude solar cycle is not considered a grand minimum, and we recover a lot of very beautiful observations from a lot of observers in the archive of scientific institution, and we have now a better shape of the solar cycle during the Maunder minimum. Another example, SAC Peak, Sacramento Peak Observatory, has a very nice collection of sunspot drawings, full disk, and otra tarea de chinos. We were reducing all these drawings, and the result is very, very good. We have a lot of observations per year, and the comparison between the sunspot number that we obtain with the SAC Peak observations and the standard, the international sunspot number, is very good, is very nice. What is the future? Well, I can read, but because it is very, very important, at least for me. We are optimistic that the coming decade will see significant improvement in our assessment of long-term solar variability and its associated uncertainty. However, this is very important, no amount of sophisticated algorithm will be a substitute for the identification and proper translation of historical documents, as well as for interdisciplinary teams involving astrophysicists, historians of science, and philologists to revisit historical observations of sunspot. The problem in our reconstruction is that our databases are poor. The future, well, in brief, this is the image of the future. We have a huge tax, and we are the ants. I think that I have time for the last part of my presentation, and I would like to show briefly this episode in the history of astronomy in Spain. You can see the Real Observatorio de Madrid, and you can see the reconstruction of the Herschel telescope. This is the big science in Spain in the early 19th century. I would like to speak about Francisco Martínez de la Escalera. We don't know nothing about these astronomers. The official biography from the book of López Arroyo on the history of this observatory only said, adjunto del astrónomo, associate professor at the Herschel Telescope Department since 1804. After the Napoleonic War, he was a professor, a teacher, at the military college established in Murcia and later moved to Jaén. No more. But remember that I am a climatologist. I was looking for meteorological data in all newspapers, and I discovered this small article, and this small article is an announcement of the sunspot that will present the sun in these years of 1818. This is the first prediction of space weather in the history. This is very nice. It's very short. Toda la vida para saber qué era esto. Su sincero servidor que sus manos besas, Francisco de la Escalera. Y luego nos preocupamos por la materia oscura. Okay, I discovered a lot of articles in newspaper by Francisco Martínez de la Escalera explaining that he discovered a phenomenon celeste, celestial phenomenon, in several newspapers. He never divulged the true nature. First, I thought, this is the solar cycle. No, it's not the solar cycle. It's more related with the position of the planets. Also, it's very important that Francisco Martínez de la Escalera observed sunspots and made meteorological observations during a lot of years. And he obtained his idea from these observations. And these observations are lost. I think that we can learn a lot of things about this episode. First, that data is better than wrong or incomplete theories, and we can ask, what do we do to preserve our observations, our data, even our hypotheses or ideas? We can also learn a lot about the nature of the solar activity cycle. The paradigm, when I was a boy, the paradigm was the solar magnetism, but in the recent years, is emerging the idea of a planetary influence, the torque of the planets in the tachoclines, and this is something, this is not astrology, this is science. We can also learn about the nature of scientific activity, because we are talking about a proposal that is, I think that is very important, but from Jaén, in a peripheral place in the scientific world at that time. Que no se enfaden los de Jaén, que yo soy de Badajoz. O sea que... And also very important about the publications and the priorities in science. Well, this is the conclusion of my talk. Very important. You have to know the past to understand the present. And with this wonderful sound dial, thank you very much for your attention.
So thank you to you, José Manuel, for the amount of work you are doing here in this history. So it's time for one question. Here there is one question. Listen.
Very nice talk. You have talked about Apelles, Christoph Schneider, and his observations just after the use of the telescope. But at the same time, there are others, like Thomas Harriot in England, or Fabricius, or Galileo himself. What about their observations, and you have studied them, and it's the beginning of the 17th century. And obviously, Appel is one and probably the more known, but there were other people looking at the sun with the first telescopes.
Yeah, it is incredible, but there are a huge number of observers in the early times. We have the classical observers, the four co-discovered of the sunspot, but there are a lot of people looking the sun with a new toy, the telescope, even in Spain and in Portugal. It is incredible. The problem is the data. You need the drawing of the solar disk, you need or a description, but in general it's very difficult to use the textual description to provide a good quantitative information about the level of the solar activity. And this is the main problem. In fact, I think that it's very important to study the people count the spot, but it's more easy. There are a spot on the sun or no? The basic information, the one dimension, no or yes. And this is, I think that this is important. A lot of works in the last year are made with the base of the active day fraction, the fraction of days with a spot in the sun. No, okay, thank you.
Thank you very much. We do not have time for more questions, so we are here. So thank you to all the speakers this session. Thank you very much.
Muchas gracias.
Directamente iniciales, tú puedes estimar, a ver, cuando has hecho la de San Fernando, es curiosidad, ¿eh?
Sí.
Pero aquí, esos picos que están a una sigma, ¿eso lo puedes contrastar con algo? ¿Tienes medidas de eclipses, de lo que sea?
Claro, sí, hay medidas de eclipses. Hay unos artículos de tu molde y esta gente que está muy bien. Esto